Okay, it all stacks up. Have y'all just changed your mind about how many folds it would take to
I
rotate?
say 9 or 10.
I'm thinking
I
seven.
think you're gonna win, Chandler, yes. 7, 9, 10, that's what I heard. Anybody else? I'm gonna try. Okay, so on 8, we had number of folds, 3 folds was what? 8, and how tall? Okay. 4 folds,
16.
and
0.064.
5 folds,
32.128.
and then 6 folds.
64.256.
Okay. All right, and then you graphed it over here, and what did it end up looking like? Okay, some kind of curve. Which curve do you think?
Exponential.
Exponential. It is exponential. Why did you choose exponential?
Is it? I don't know.
Actually goes up faster, doesn't it? Because it's going up. See how much faster it goes up? Huh? What, Drew?
Rapidly.
Yes, it went up rapidly. Okay. What's the independent variable on this one?
Independent is the number of folds.
Number of folds. And dependent?
Is the number of pieces.
Pieces. So the number of pieces of paper depends on how many times you fold and cut it, right? Does that make sense? Okay. Now we're going to come up with an equation for this curve or this table right here. Any ideas how we could come up with the equation? Stat, edit? Okay, let's do that. Everybody got a calculator? Okay. We're going to put it in stat, edit, so stat, edit, 0 through 6, and L1, and then we'll put the number of pieces in L2. It's already in yours. Emmett is already in yours, yeah, because we did it second period.
Except for I didn't realize it.
Now you cleared it, and now you have to redo it. Okay, if we think it's exponential, are we going to do linear regression?
No, X spread 0.
Right. Okay. Has everybody got it in? Y'all have it entered in already? Did yours entered in already? Okay. Let's go to Stat Calc. And there's linear regression, quadratic regression, cubic regression, portrait regression. And then if you keep going down, we get to exponential regression. It's on 0. Now push enter. And push enter again. Okay, so we've got y equals
2.
to the x. Let's write that
Does
down.
anybody else do the function?
Y equals 1 times 2 to the x. Okay. Okay, then how did we get this? What did we just do? What's that called? Okay, we did stat edit, and then we did
Stat count.
exponential regression. EXPREG is what I should have put. Okay, and what was A? A was what?
1,
1, and B was?
2.
Okay, let's look back at the table and see if we know where these came from. Before we did tax, we were working on this. Now, if you remember or not, but what the A is, where it starts, remember that? And then the B was
How
the
much is
ratio. Yeah, what you're multiplying by. What are we multiplying by every time?
2.
2. It's doubling every time, isn't it? Okay, so your starting point is your A, and what it's multiplying by is your B, or your ratio. Remember when we did that before? Yeah, okay. So, when we find the equation for the next one, let's not use stat edit. Let's see if we can figure it out. We're going to have y equals, what would A be for this one over here?
2. Or 0.04.
Point
Oh,
004 would be A. And how about B?
2.
Okay, because you're multiplying by 2. Is that right? 0.02 is 0.008 times 2 is 0.16. Okay, so how would you write that equation?
Y equals 0.0 times 2x.
There you go. Okay, so what's the independent for this graph?
Fold.
And the dependent?
Thickness.
Okay, the thickness of the stack, right? Okay. I'm going to put height just to height of the stack. So the height of the stack depends on how many times you fold and cut it. Okay, what function rule relates these? We're going to put exponential here. Probably wondering why we're doing exponential when the whole thing is about logarithms, but you'll see here in a little bit. Okay. Okay, how do the functions for the number of pieces and the thickness of the stack compare? Which parameters are alike and which are different? What they mean is which parts of the equation are the same and which ones are different.
2.
Okay, the 2 is the same.
B is the same.
B is the same. Okay. B is the same because the ratio is 2 for both functions. Or you could say both functions double every time. Okay, what part's different? The A. The A is different because they start at different points. Because the functions start at different points. The number of pieces started at 1 and the height started at 0.004. Okay, now we're going to find out how many times did you have to fold and cut the stack of paper to make it as thick as a textbook. Okay, so to do that, we're going to take the equation that we did for height. What equation did we get for height? Remember?
0.004 times 2x.
Good. Okay, put that in Y1. 0.004 parentheses 2x. Go to the table. It should match your table. So my table's not starting at the right place. How's yours? It starts. Okay. I'm going to go to table start, which is second window, and start it at 0. And I want the change in the table to go by 1s. Okay. Now it looks like our table, doesn't it? Does yours look like this? 0, 0.004, 1, 0.008, 2.016. Okay, the question is, how many folds or cuts does it take to get it as thick as a textbook, which is a little more than 2 inches? Go to where Y1 equals 2 inches. And so how many is it? 9. 9 folds or cuts. Does that make sense? After we cut the pieces of paper and stacked them? Okay. All right, a student is 5 feet 5 inches tall. How many times would you have to fold and cut the stack of paper to make it as tall as she is? Well, how tall is she in inches?
Oh,
How much?
12 times 60.
60 plus 5. Okay. So she's 65 inches tall.
Wait, 14.
Yes, it would. 14 cuts.
That's crazy.
I know. And it is, isn't it?
I want to do 14 cuts now.
It's because it's doubling every time. So it gets big fast. Okay. All right, how about suppose the ceiling is 11 feet high. How many inches is that?
11
11 times 132.
So about
It's just one more, isn't it?
it's a little more.
Well, it said, what is the maximum number of times you could fold and cut the stack of paper so that it would still fit under the ceiling?
15.
So 15. Yeah. 15 cuts and it would go to the ceiling. That is crazy. But it's true.
I don't think so.
Okay, well here, let me show you this one. We put two groups together. This is 7 cuts right here. Okay, and then it would double, then that would double, and then that would double, and that would double. You see how it's getting big fast? Okay, here this would be 8.
Can we put all of ours together?
Yeah, it'll be about like this.
And how many?
Okay, so like this is 7
We have
cuts.
2 groups.
This is
We
8
made
cuts. This would probably be 9. Actually, that's supposed to be a textbook. Well, our paper's different than theirs. 9, 10, 11. See how we're getting close to a person. Twice that. It's almost a person.
But a person's only supposed to be 14.
Okay, well,
Yes, you
you know,
have
I'm
one.
estimating quite a bit here. Okay. Just trying to give you an idea. This is 7. This would be 8, 9. Probably go a little too high. 10. Okay. 11. That doubles. I'm trying to go too high. All right. It would work. All right. Now we're going to do something a little different. It says summarize this information from problems 5, 6, and 7 in the table and graph below. Notice that in this case, the x values represent the thickness of the stack, and the y values are the number of folds. Okay, so what happened here? How is that different from the first table we had?
This one starts at 0, not 1.
Well, that one started at 0.
No, they're going to be opposite. It's going to be opposite of what it looked like the first time. It's going to go
What's
this side.
opposite?
The x and y.
The x and y's are what happened to them?
They flipped.
They flip. They're switched, aren't they? We've got thickness for x and number of folds for y. Okay. So now for the book, how thick was the book?
2 inches.
And how many folds did it take? 9. And then the person
65.
and
14.
then the ceiling
132.
and 15. Okay, so we have switched the x and the y. The independent and the dependent variables have switched. So we're going to graph this. 0.004 and 0 is right here. Okay, 65, 2 and 9, sorry. Somewhere like this. 65 and 14. 132 and 15. Okay, then we'll connect it as best we can here. Does this look like a function? Logarithm. Okay. So the one that we haven't studied yet, it's our last one. Okay. It's the logarithm function. Okay. How does this curve or this graph compare to the one in problem 3?
It's the same, it's flipped over.
It's flipped over what? What is it flipped
Flipped
over?
over to
X,
the
Y.
left.
Right, well,
X.
y equals x. Good. Okay. It is. It's flipped over y equals x, or reflected over y equals x. And it did that because we switched x and y. What happens when you switch x and y and you flip it over y equals x? What is that called? Remember? Starts with an I?
Conversion.
Close. Inverse. Remember inverses? You switch x and y, or you flip it over the line y equals x, which is something going through here somewhere. Okay, so a logarithm function is the inverse of a what?
Exponential.
Exponential. They're